Hello! Today we're going to be picking up talking about testing prime numbers. I'm bouncing around the lecture notes a little bit, so the majority of this material comes from lecture 13 in our Total Notes PDF. The material on the sieve of Eratosthenes is not in those lecture notes. As usual, I'll have a copy of these slides up on our website. The layout for today, I want to talk about a couple different tests for identifying prime numbers, or equivalently, tests for identifying composite numbers. The first one of these I'll be talking about is the sieve of Eratosthenes. This is a very old algorithm, about 2,300 years old, about. And then as we explore other tests for prime and composite numbers, we'll get into the idea of pseudoprimes. Last time we left off after some discussion, about a week, on the RSA encryption protocol. Remember that in RSA encryption, we've picked some large modulus n. N is the product of two different prime numbers, P and Q, and the rest of this we've already seen before. Our messages we want to be encrypting are just going to be residues mod n. We can pick any key, which is just some exponent relatively prime to phi of n. You can look at other lecture recordings for that information. The big idea coming out of our previous lecture was that we want P and Q to be two very large prime numbers, but we also don't want them to be too close together. The idea I put forward was we're going to pick P and Q at random, but then how do we pick a random prime number? I was saying, well, let's just pick a random number to start with, and if it's prime, that's great. If it's not prime, then we'll keep going until we do find a prime. In today's lecture, I'm going to be talking about how do we find those prime numbers, exactly what algebraic tests can we be using on them, and in a future lecture, I'll talk a bit about how practical that is. So how many numbers will I have to go through before it's likely that I do find a prime number? So just to refresh our definition for prime number, an integer p is prime if it is not divisible by any integer between 1 and p, and that is exclusive. So I know that any integer p is divisible by 1, it's divisible by itself. I'm looking for any other prime factors this number could have. So the first test I can think of is, this is the worst you could do, really. Just brute force the thing. I can list out all of the integers starting at 2 up to p take 1. Those are the only numbers that could possibly be factors of p. If any of those numbers do divide p, then I can stop, because then I've got some non-trivial factor of p. P has to be a composite number. If I go through the entire list and I don't find any integers that divide into p, that's the definition of being a prime number. So run through the whole list. If nothing in there divides p, then I know definitely p is a prime number. So this is a test that will always work, but it's not a very practical test. Remember, I'm picking these prime numbers to have, maybe 100 digits, maybe 1,000 digits, maybe 10,000 digits. I want them to be so large that finding the factorization just by brute force is impractical. But that's exactly what this test is doing. It's just trying to brute force to find a factorization of p. So this can work for trying to find out if, say, 137 is prime, but for the size of numbers that we're talking about, this test is not going to cut it. Now, if we work smarter, we can exclude some of those divisors that we're checking and save ourselves a significant amount of effort. This is our lemma from the previous lecture. If I have some integer n, which is composite, at least one of its prime factors has to be less than or equal to the square root of n. So in my test, in my brute force test I was just describing, I only need to go up to the square root of p. Remember, p is the number that I am checking to see whether or not it is prime. If I list out all the integers from 2 up to the square root of p, those are divisors I can check. If any of them divide p, then p is composite. But if none of those integers divide into p, then the lemma tells me that p has to be prime. Composite numbers always have at least one prime divisor less than their square root. We've run through all the potential numbers up to the square root of p, didn't find any that actually divide into p. That means p has to be a prime number. Again, this is a test that will work every single time, but I still have this question in the back of my head, is this a practical test? Again, I'm trying to pick an integer p so that prime factorization is impractical. It is so large that just trying to brute force and find all the factors will not be finished within the lifetime of any person that wants to break my encryption. Now, if I have some 1,000-digit prime number p, how many digits does its square root have? Well, on average, half the digits, so it'll be some 500-digit number. That's still a lot of things to check. And for the fact that I know that this kind of test is available to my opponents, people I don't want reading my encryption, if I'm able to calculate this for my prime p, then my opponent will also be able to calculate it for my modulus n in the RSA encryption. So for the integers that I'm talking about, this test is still not practical, even though it's something that will work every single time. It just takes so long to do. There's no point in doing that for practical purposes. A lot of times in mathematics, we know stuff exists, it's gotta be out there, or such and such algorithm must eventually stop. But in the long run, we're all dead. Now, I got my second test here by thinking about which numbers I actually have to check. I only have to go up to the square root of p, but there's still some numbers on here that I don't have to check. Let's say that I try to divide by 2. I find out that 2 does not divide p. That's great. Then my next step is to check 3, and then the step after that is to check 4. But I already did 2. If a number is not divisible by 2, it's not even. And if it's not divisible by 2, it's certainly not divisible by 4. This test says check all of those integers, but there's redundancies. So what's the bare minimum that I have to do for this test? How can I save myself more work here? Now, this is a very old idea. So we're going to bank on unique factorization, or the fundamental theorem of arithmetic, if you prefer to call things by theorem names. I know that all integers have a unique factorization into primes. I think that this number p is a prime number. I hope so. That means that its prime factorization is just p. There's no other prime numbers that divide into p. So, if I list all the numbers from 2 up to square root of p, I only actually need to check the prime numbers. So let's do that. Let's list every single prime number from 2 up to the square root of p. If I have that list, I can check all of those primes, whether or not they divide p. And I can do that, well, I can just punch in my calculator, see if I get a whole number. That's one way to do it. As we get to larger and larger primes, I'd probably be using the Euclidean algorithm to calculate their GCD. If I get a GCD 0, I know, if I get a GCD of, call some integer in here n. If I get a GCD of n, then I know n divides p. Right. So I'm going to list all of these primes out. If any of them divide p, then p itself has to be composite. If none of them divide p, then p actually has to be prime, because a composite number will always have at least one of these prime factors less than its own square root, or equal to. But I've got myself into a bit of a chicken and egg situation. I can determine whether or not p is a prime number as long as I know what are the primes from 2 up to the square root of p. Okay, that's great. I'm going to pick some number in here. Is it prime, right? I say, okay, I know 2 is prime. I know 3 is prime. I know 5 is prime. I get out to the end of this list. I get up to starting to hit up on square root of p. How do I know that the number that comes before square root of p is prime? Well, I could go back and I could list out all the factors and I could try to figure out if the number before square root of p is prime. And it's a smaller number. It's less to check. But I'm still getting myself stuck up on this situation. So I want a nice, clean way to list out all of those prime numbers at once without duplicating my effort. I'm trying to make this as easy on myself as possible. So here's the actual version of test 3. This is an algorithm, again, about 2,300 years old, called the Sieve of Eratosthenes. Eratosthenes was an ancient Greek mathematician. He lived a little bit after Euclid. He's also famous for calculating the curvature of the Earth based on the lengths of shadows in wells and off of obelisks and stuff. Same guy. Pretty cool stuff. He also did number theory. So this is his algorithm. Step 1. We're going to list all the integers from 2 up to p. As we follow through the steps of the sieve, we're going to remove all of the composite numbers from the list, and then with all the composite numbers gone, everything that's still on the list must be a prime number. Okay. What are the steps? So we've listed out all the numbers from 2 up to p. Starting with the number 4, strike out every second number on the list. Those are going to be all the even numbers. 2, 6, 8, 10, 12. Cool. They're gone. I already know they're composite. Get rid of them. Go away. What's the next step I do? So 2 is still on my list. The next smallest number is 3. And my notes say that's got to be prime. Well, yes, I know 3 is a prime. Thank you very much. Now I'm going to start with 6. I already did strike out 6 because I know 6 is even, but I left it there as a placeholder. You'll see on the next slide what I mean. Starting with 6, I'm going to strike out every third number on the list. So get rid of 6. 6 is already gone. Get rid of 9. 9 is composite. Get rid of 12. Get rid of 15. Get rid of 18. Those are all composite numbers. Be gone. Cool. So we go through the whole list that way. What's the next thing I do? The next smallest number is 5. 5 must be a prime. Yes, sounds good. Starting with 10, strike out every fifth number on the list. The cool thing about this algorithm is I don't actually have to check division, right? I can just count by 5s. I can do that very simply. Okay, so we're going through this algorithm. At some point, call it step n, the next smallest number on my list, I don't know what number that is because I don't have my list in front of me. I'll just call it Q. This Q must be prime because it's the next smallest number on my list, and I already crossed out all of the composite numbers before I got to Q. I start with 2Q, so 2 times Q. That's a composite number. Get rid of it. And then strike out every Qth number on the list. So yes, every, 1 out of every Q of those numbers. Those are all multiples of Q, which means those are all composite, which means those are all off the list. Don't want them. And we keep on going. So this is sort of the generic step. Take the next smallest number on the list you haven't sieved out by, go to its double, strike out every Q, 1 out of every Q numbers after that. When do we stop? After we sieve up to the square root of p, all the numbers not struck out yet have to be prime. How do I know that? Well, again, I know that any of those numbers, if they were composite, they would have a prime number less than their own square root. That square root of some random number on the list has to be less than the square root of p, and I already got rid of all multiples of all prime numbers less than the square root of p. At that point, I'm done. My list is complete. As an example, here is a list of all the integers from 2 up to 30. I left out 1. 1 is not prime. 1 is a unit. So find all the prime numbers from 2 to 30. The smallest number on my list is a prime number. Yes, it's 2. I'm going to start at 4 and strike out every other number. So that looks like this. So 4 is gone, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30 are all composite numbers, and they are all struck from the list. I'm going to leave these as placeholders to make my next step of the algorithm a little bit easier on myself. I can do that. I like making things easy. So, what do? I was just at 2. I go to the next smallest number, which is 3. And again, 3 is a prime number. So I start at 6. 6 is a multiple of 3. I should cross that out again, I guess. Go up 1, 2, 3. 9 is composite. 1, 2, 3. 12 is composite. 1, 2, 3. 15 is composite, and so on. And I'm just going to strike all of those numbers out. I don't even need to check any GCDs or division. I just know that if you start at 6 and you go up by 3, you still have a multiple of 3. If you start at 9 and you go up by 3, you still have a multiple of 3. It's super simple to do. So I strike out all of the multiples of 3 from the list, and now I have this. Okay. My next smallest number on the list is 5, and I'm going to start at 5, say, okay, 10 is composite, go up 1, 2, 3, 4, 5. 15 is composite, 1, 2, 3, 4, 5. 20 is composite, 1, 2, 3, 4, 5, 25 is composite, and so on. I strike out all those, and I get this. When do I stop? The square root of 30 is 5.47 and change, which isn't an integer. So I can stop at p equals 5, which is real good because those are all the numbers I've sieved out by. And now everything that's on this list, but not struck out, must be a prime number for exactly the reasons I said about 4 slides ago. So the prime numbers between 2 and 30 are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. That's it. So we ended up finding all of the prime numbers between 2 and 30, but we did it in a way that was very quick and didn't have us recalculating lots of GCDs and divisions over and over again. So this is the sieve of Eratosthenes, and this is, again, something that I expect you to be able to reproduce. So, for example, if I give you a list of the integers between 2 and 100, it's not unreasonable for me to ask, use the sieve of Eratosthenes to find all the prime numbers between 2 and 100. How far do I have to go? Well, the square root of 100 is 10, so after you sieve out all the way up to 10, you're done. Just 10 steps. That's all that I'm asking for. And then you, too, can calculate every prime number between 2 and 100. So, we got some ancient history today. That's pretty cool stuff. As I was saying, this is one of the tests we expect our attackers to know. And so for the prime numbers we are interested in, this still does not cut it for identifying prime numbers. If I can use this test to tell me whether or not my prime number p actually is prime, my attacker can also use this test to factor my n, break my encryption, read all of my secrets, and I don't want that. So instead of just brute forcing the factors, and instead of sieving, let's try to use some of the stuff that we learned from modular arithmetic. We've been seeing differences between the prime numbers and the composite numbers when we multiply in the integers mod n. Maybe we can use some of those techniques to help find when is a number composite versus when is it prime. If I can just run a test that I know only works for prime numbers, and I have an integer n that passes it, it should be prime, right? Right? That makes sense. So what do we know about prime numbers and modular arithmetic? What makes prime numbers special? Let's go back a couple weeks when we talked about Fermat's little theorem. Now this is also Euler's theorem, but Euler's theorem works for composite numbers. Fermat's little theorem is just for primes. If p is a prime number and a is any integer in, typo, z mod pz cross. If a is any one of those integers that does not share a common factor with p, then a to the p take 1 power has got to be 1 modulo p. Like, obviously, 0 to any power is never going to be 1, so that's that's what's up with this typo. I'll fix that for the slides I post on the website. Euler's version of this theorem for composite numbers is different. Euler's theorem says a to the power phi of n. And it just happens that for primes, phi of n is p take 1. But if I have some number whose factorization I don't know, if I have some mystery integer, I can calculate p take 1, and I don't know whether or not that's the Euler phi function, because I don't know whether or not this number is prime. So my test number 4, my idea is I'll pick some random a from the set z mod pz, should be a cross there, and calculate a to the power p take 1 mod p. If I do get 1, then I have verified Fermat's little theorem, right? I'm supposed to get 1. Does it actually mean I've got a prime number? Well, the contrapositive doesn't quite work like that. But if I don't get 1, I definitely know that P is composite, right? I follow this equation just like Fermat says. I didn't get 1, so that means P can't be a prime number, right? That's the setup to this theorem. Let's check. So I'm going to look at the number 51. That's the number I'm going to test. I know that 51 minus 1 is 50, so that's the exponent I'm going to use. And I'm going to check the number 2. And when I calculate 2 to the power 50, modulo 51, I get 4. I didn't get 1. Well, that's great. That means that if 51 was prime, that would mean that Fermat's theorem was broken. But I'm going to conclude from this that 51 is not prime. In fact, it's divisible by 3. Just like that, 3 and 17. Now there's a bit of a problem. I've been hinting at this for the past slide or so. You gotta pick a good residue to check, because sometimes this test can give you a false positive. I can check Fermat's equation. It looks like I got it right, but my modulus still isn't prime. So for example, if I didn't do 2 to the power 50, let's say I do 16 to the power 50, then that, I'll tell you, is going to reduce to 1 modulo 51. So it looks like Fermat's equation worked. I mean, this is certainly a congruence. This is a true statement. But 51 still is not a prime number. So the takeaway from this is that there are composite numbers that will sometimes pass through Fermat's little theorem as though they were prime. And that is potentially a problem. I don't actually have a formulaic way to pick a good A to tell me whether or not integers are composite. So 2 can tell me that 51 is composite, if I couldn't already factor it myself. But 61 says, hey, this 51 kind of looks like a prime. That is a really strange phenomenon, and it's one that we're going to give a name to. So if I do have one of these residues A, and I need to pick an A, again, with GCD of A and N equals 1, which is to say A and N are relatively prime. They do not share any prime factors. If I have these two numbers A and N, and it is the case that Fermat's equation works, that A to the power N take 1 gives me 1 mod N, the name for that, is that n is a base A pseudoprime. So let's go back a slide. 51 passes the test when I look at 16. So 51 is a base 16 pseudoprime. That's how I would say that. So let's update this test. See if we can make it better. Again, pick some A, some residue in there. I'm going to check its GCD first, right? That's a simple thing to do. I can just use Euclid's algorithm. Very quick calculation. If I do Euclid's algorithm and I don't get 1, then I've got some common factor between A and P, which automatically tells me P is composite. Okay. So step number 1 is I'm going to check this GCD just to make sure. It's a nice insanity check. Otherwise, I pass the GCD test, so I still have A to the n take 1 on the table. So I'm going to calculate, well, my number's P, so I'm going to calculate A to the power P take 1 modulo P. If I don't get the number 1 back, then P has to be composite. If I do get 1 mod P, then that tells me that P is a base A pseudoprime. P is almost a prime. I don't have enough information to say whether it's an actual prime, but as far as the residue A is concerned, P is good enough to make Fermat's little theorem work. So, okay, cool. We're getting there. Can we fix this? It should be, if I have a composite number, sometimes it will be a pseudoprime, and I don't like that. I want to quickly identify my composite numbers and get rid of them. So there should just be some base that identifies P as composite, right? I just have to pick the right base A, and then that base will tell me my number's composite, throw it away, keep looking for some other prime number, because this one ain't it. That's the goal. But I got some bad news about that. Here is an example. I'm going to pick my own integer, capital N. I'll tell you for free what the factorization is. N is 561. And 561 factors as 3 times 11 times 17. Cool. And let's say that I want to check it to the base A. Is 561 a base A pseudoprime? Dunno. Do I get 1? Well, I'm working generically. I don't have an actual integer A here. But there's a weird thing about 561 that's not obvious. If I look at this factorization, 3 and 11 and 17, the Euler phi function of 3 is 2, right? The prime number, Euler phi, is number of residues relatively prime to 3. There's only 2 of those. And 2 divides into 560. I can do the same thing with 11. The Euler phi function of 11 is 10, and 10 divides into 560. Phi of 17 is 16, and 16 divides into 560. 560 is, in fact, 16 times 35. Is that bad? The phi function is my special number that makes exponents mod n easy. So my number that makes exponents mod 3 easy divides 560. My number that makes exponents mod 11 easy divides 560. My exponent that makes multiplying mod 17 easy divides 560. That's a weird thing. What does that mean for my problem? Again, I have A is some residue, relatively prime to 561. Those are the ones I can actually multiply and get back to 1. Then A is also relatively prime to each of these prime factors, 3, 11, and 17, right? None of the factors of A can be a 3, an 11, or a 17, so my A is also going to be a unit mod those other primes. And again, I have another typo. These should be exponents, so I will correct that on the published version of these slides. So what this equation should be telling us is A raised to the power 560 mod 3. Well, that's the same thing as A squared and then raising A squared to the power 280. But A squared is 1 mod 3, so the stuff in parentheses is 1. 1 to the power 280 is still 1, so I get 1 mod 3. So this is almost the Fermat equation, except I'm supposed to have a 561 here. I did it mod 3. So I can pass the Fermat equation mod 3. Let's do that for 11 as well. A to the power 560 I can rewrite as A to the power 10 to the power of 56. 10 was the exponent that makes A 1 modulo 11. So A to the power 10 is equivalent to 1 modulo 11. And again, 1 to the power 56 is 1. So I have passed the Fermat equation mod 11. And again for 17. A to the power 560 is the same as A to the power 16 to the power 35. A to the power 16 has got to be 1 mod 17, so this stuff in parentheses is 1. I've got 1 to the power 35, which is just 1. So I have now, no matter what my A is, no matter what it is, it will pass the Fermat equation, but not to the, not mod 561. It'll be mod all the different prime factors of 561. And that's bad. I have an equation that says A to the 560 is 1 mod something. A to the 560 is 1 mod something else. A to the 560 is 1 mod a third thing. Okay, yeah, they are 3, 11, and 17. Those are all relatively prime because they are different prime numbers, which means the Chinese remainder theorem kicks in. I can find a solution that solves all 3 of these congruences, and that solution is going to be a residue mod 561. So I can glue all 3 of these congruences back together and say A to the power 560 is 1 modulo 561. So no matter which unit I picked, no matter what A I have, A says, yeah, that 561 seems like a prime kind of guy. So what does that mean? 561 is a base A pseudoprime for every possible base you could throw at it. Even though we already know that 561 is composite. Well, that's just kind of the end of it, isn't it? There are numbers that will pass this test no matter what residue we look at. There's no way to be smart about which residue A we're testing with. There's a special name for these kinds of numbers. The definition: if n is an integer greater than 2, and it's a base A pseudoprime for every residue A that's relatively prime to n. The name for that is that n is an absolute pseudoprime. It doesn't matter what base you look at, n is a pseudoprime. Another name for these is Carmichael. Carmichael was a mathematician who worked towards the beginning of the 20th century, conjectured that there should be infinitely many absolute pseudoprimes, and that is true. There are infinitely many composite numbers that will pass through this test as though they were prime numbers. So, for his work on the subject, we call these Carmichael numbers. And there are infinitely many of them. So, 561 is the smallest Carmichael number. The next ones up are 1105, 1729, which is famous for other reasons, if you've seen that before, 2465, and so on. Just for laughs, you can find a list of these numbers on the online encyclopedia of integer sequences, number A002997. So link right here, or just type that into your browser. But these Carmichael numbers, these absolute pseudoprimes, are the numbers that are going to foil our attempts at testing primality. We'll only be able to discover them if we accidentally land on something that shares a common factor with n. Otherwise, we'll have no way of detecting it. At least, we'll have no way of detecting it using Fermat's little theorem, using this a to the power p take 1 equation. So, next lecture, we're going to look at another test for prime numbers, one that does not have pseudoprimes. All right, well, thanks as always for sticking with me. If you have any questions, you can, if you're one of my students watching this, you can send me an email or respond on Moodle. If you're a member of the general public, I hope you're enjoying this stuff. Feel free to leave a comment, and I will try to respond to you if you have any questions about this. But for my students, please do email. It makes things much easier for me to have it all in one spot. Bye.